Hi all, welcome, and thanks for taking the time to have a look at this. I've come up with an experiment to test exactly whether the Earth is round as a ball or flat like a disc, and I'd like your opinion on it. So feel free to share something in the comment. Take a look. It doesn't matter what perspective, if you're from a ball Earth perspective or from a flat Earth perspective. I think this is going to be good for both of us. Imagine, if you like, we had a pipeline. And this pipeline was running parallel to the Earth, right around the Earth. And then in the pipeline, we filled it up halfway. So only half of the pipe filled with water. Obviously, because of gravity, the water will be on the bottom half of the pipe, not on the sky side, but on the Earth side. Now imagine if we had a look at this pipeline from a little bit further away from the Earth. Here you can see the pipeline around the Earth, and the water obviously in blue, and on the right hand side that small little image showing you the water halfway inside the pipe. Right, now how would gravity act on that water? Well, we could assume that if we pull all the water inward down to the ground towards the center of mass, the center of the Earth. Now, would the principle be the same if the pipe was only a quarter of the distance of the Earth? Remember, the whole of the Earth, we know that the water is going to pull all the way down to the ground. What about if it was only a quarter of the Earth? Would gravity still act the same on the water? Think about it. The water, if you stood next to the pipe and you could see in, you'd see the water level by that blue line over there. Now, it was a quarter of the Earth. Would gravity still act the same on the water? Obviously, we'd block both ends halfway so that the water wouldn't run out. What if it was less than a quarter of the Earth? What if it was only 1 kilometer long? Obviously, we can calculate there is some curvature after 1 kilometer. Obviously not very much, but there is some. So what if it was only 1 kilometer long? Would gravity still act the same on the water level? What do you think? Remember, water on the side of the ground, not on the side of the sky. So would the water stay at the bottom of the pipe? There's another way of looking at it. Got the Earth on the bottom, and on the top you can clearly see the pipe with half full of water. What would happen if we were to lift the end of the pipe, the lowest end of the pipe? If we lifted it up, what would happen to that water in the pipe? Well, obviously it's still going to try and conform to gravity. Remember, bend down, it's going to look like that. So half the pipe on the left and half the pipe on the right will be equal heights of water. But if we lifted the pipe up on the right hand side, there will be less water on the right and more on the left. Does this make logic sense? So that means if the Earth were a globe and we had a pipe and it was bent to the curvature of the Earth, if we then lifted the pipe so that it was a straight pipe, not parallel to the Earth, just a straight pipe, then the water on the right will be less than the water on the left. If the Earth was flat, the water would be the same height on the left and right hand side of the pipe. What do you think? Alright, let's re-look at this idea of lifting the pipe and seeing what the effect of the water will be. If you take a bottle and put some water in a bottle, and then you lift the one side of the bottle up and down, you'll notice that the water always remains parallel to the Earth. And this is what we'll do with the pipe. Just lift the one end of the pipe so that the pipe will be a straight pipe and not bent round the curvature of the Earth, parallel to the Earth. Does that make sense? Right, let's look at this from the globe perspective first. If we've got our straight pipe, the water on the right is lower than the water on the left. Now on each end, remember, we've blocked both ends halfway. So the water on the right side of the pipe wouldn't even come to the top of the end cap. The water on the left will be exactly level with the end cap. Now it wouldn't matter how much water we put in on the right hand side of the pipe, the water level will never increase. The excess water would just overflow on the left hand side. Right, now let's look at it from the point of view of a flat earth. So you've got your pipe, it's level, and the water is level both ends. Do you see how that will work? Right, so what will happen if we now bend the pipe to be parallel to the curvature of the earth? How would that impact on the water? Well, obviously the water on the left will reduce and the water on the right will increase because the water is always level. Obviously then the water on the right will exceed the height of the end caps and literally just flow out. And eventually we'll end up with just a small little bit of water at the end of the pipe. So now considering our pipe with all the water in the pipe halfway up and the end caps blocked halfway up the pipe, what would the situation look like if we were to bend this pipe down to match the curvature of the earth? Bend it down to match the curvature of the earth. What would happen? Well, obviously the water will just run out. Well then, we could all just have a nice big glass of truth. Now whether you like it or not, if water is in a pipe, or in a lake, or in an ocean, water is always level. The earth is flat. Come to terms with it. Time is up. So how much curvature is there? And how can we calculate the curvature? Alright, let's look at how we can calculate the curvature and how we can practically achieve this experiment. If you look at the diagram, R is the radius of Earth, B will be the length of pipe along the curvature of the Earth, A is the angle from the start point where the line from the center of the Earth intersects with the end of the pipe. V1 is the distance from the horizontal line from the start of the pipe to the Earth at 90 degrees. V2 is the height that the pipe will need to bend down in order to get it parallel to the Earth at the end of the pipe. H is the length from the center of the Earth to the horizontal of the start point of the line intersecting at the end of the pipe. The first thing we need to do is find out what the radius of Earth is before we can get to the curvature calculation. Now using the formula on the right, we can calculate that if we had a pipe 1 kilometer long, then there would be a 7.8 centimeter or 78 millimeter difference between the start of the pipe and the end of the pipe in height. So there's our pipe 1 kilometer long. The start point, the start of the arrow, and the end point, the end of the arrow. There will be a height difference from the start point to the end point of 7.8 centimeters. Now in order to make this experiment 100% accurate, there's a few other things you need to take into consideration. One being your height above sea level. Obviously these calculations that I've shown you so far will work 100% at sea level, but if you're above sea level, obviously you have to take that into account as well. Also, the height of the pipe above the earth. So if your pipe is situated 1 meter above the earth, that will have to be factored in as well. Right, to get your height above sea level, open Google Earth, zoom into the area that you are going to do your experiment at, and click on the show ruler icon. Right, then the ruler window will open, and there you can select whether you want the measurement to be done in kilometers or miles or centimeters or meters or whatever your choice is. Okay, so I've chosen an area in Johannesburg, reason being it's up on a plateau and it has a nice height above sea level. I thought I'd give you Globers the benefit of the doubt, just to show you that up at an elevated position there's still significant curvature. So click on the area where you want to start your experiment, and then click on the area where you want to end your experiment. I'll make it roughly about a kilometer. There we go, 1 kilometer. Then click on the save button and click OK. Now if you right click on the line that you just saved and select Show Elevation Profile, a little pane opens up at the bottom, and as you move your mouse along from left to right or up or down on your line, there you can see the height in meters above sea level. So now let's apply that to our formula. We will add the height above sea level to the radius of the Earth, and also additional meter for the height of the pipe above the Earth. And as you can see over there, our V2 is 8.2849 centimeters. So in our pipe, a meter above the Earth with an additional factor of 1.766 kilometers, because of the height above sea level, we still end up with an 8.2 centimeter fall. Now we build pipelines all over the show, in your cities, sewer lines, pipelines for all sorts of stuff. And the guys that do that are the architects, the civil engineers, and the surveyors. And I encourage you, go and talk to them, show them this video, and blow their minds, because as soon as they finish watching this video, they will instantly be flat earthers. There is no ways that they take the curvature of the Earth into account in any of their projects. Ask them. Now, building a pipeline can be a little complex, and it can also take something that most of us don't have, and that is money. So the following experiment is low budget, but will give you the exact same resultant, and that is the Earth is flat. What you require is 2 water containers and enough hose that you can achieve at least 1 kilometer in length, or 1 mile if you prefer to do it in miles. What you'll need to do to start is get your 2 water containers, place them side by side, and mark them evenly so that they both have a mark on them at the same height. You'll also need to remove both lids. This experiment works on the principle that you learnt about in high school, being that if you have 2 or more containers and they are joined, that the water level will always be uniform. What that means is that on a globe, if you have one water container a mile apart from another or a kilometer apart from another, the water level will be at the same height. There would, however, be a difference in the height of the one can to the other because of the curvature of the Earth. And that height would exactly be able to be calculated by your curvature calculation. So by using our curvature calculation that we had before, we know exactly what height to position the second water can. And that is 8.2 centimeters lower than the first. Now after you've positioned your water containers, and if the water level remains the same height in the can, then you've got nothing to worry about, the Earth is round. If however the water decreases slightly in this can, and you need to top it up to match your water line, and if it increases in this can, then you have a problem because the Earth is flat. Alright guys, thanks for watching. I hope this has been helpful, and I'd like to encourage you, do your own experiments, find out for yourself. Don't listen to this one or that one, just do your own experiments. That's the only way you'll know for sure. Peace out.